If descriptive statistics are the easy statistics, the simple ones, like mean, median, and mode, or standard deviation and range, then inferential statistics are the more high-powered, the more sophisticated statistics. And these are the statistics that allow us to make an inferential leap from the data that we have collected and summarized from our sample to the overall population. They allow us to generalize from the data collected from the sample to the overall population. So this all goes back to the logic of sampling. And inferential statistics tend to assume that the sample that you are studying is representative of the overall population, which tends to be true if your sample is a random sample. So inferential statistics are not as applicable when you are dealing with convenience or purposive or snowball samples. Sometimes we might still use inferential statistics in those cases, but inferential statistics tend to assume that the sample you have studied is representative of the overall population. So let's say, for example, that you are a company and you're trying to determine whether your customers prefer product A or product B. And let's say that you decided to do a survey to ask them to compare the two products. You know, maybe rate product A on a scale of 1 to 10, rate product B on a scale of 1 to 10. And you realize that you're not going to be able to administer this survey to all of your customers. You're not going to be able, you don't have the time or the resources to distribute the survey to the entire population of customers. So instead, you only distribute it to a sample of your customers. Okay, so your sample of customers takes the survey, and then you compile the data, you analyze the data, you run some statistical tests, and you come up with some means and standard deviations. Maybe you discover that the mean score for product A was 8.3, and the mean score for product B was 5.1. Now, you might be tempted to say, okay, I have just proven that our customers prefer product A over product B. Well, first of all, we never use the word prove in research because nothing is ever 100% definitive. All of our findings are always subject to revision and further research. So we want to scratch that word prove. But even if you were to use the word prove, at best, you have maybe been able to prove that the sample of customers that you studied preferred product A to product B. But what you want to know is whether all of your customers would prefer product A over product B. You want to be able to make that inference, that inferential leap. You want to be able to generalize from the sample you studied to the overall population. How can you do that? Well, that's the beauty of inferential statistics, is that they can tell you whether or not you should have confidence that the results you obtained from your sample would in fact apply to the population at large. So inferential statistics tell us that likelihood, the likelihood that the results for our sample would apply to the full population. Now, another thing that inferential statistics allow us to do is they allow us to examine relationships between variables. So if you have an independent variable and a dependent variable, and you want to see how the two variables work together, inferential statistics will allow you to look at some of those relationships. So inferential statistics, there's a bunch of them. Some of the more common ones are correlations, t-tests, ANOVA, which stands for analysis of variance, and regression. If this were a longer or more sophisticated research methods course, we would get into some of those inferential statistics. Or if you take a stats course, you will learn about some of those inferential statistics. But for our purposes, we're not going to go into all of those individual inferential statistical tests. Instead, we're just going to talk about the general logic of how inferential statistics work. So no matter what kind of an inferential statistic you run, it is going to produce a p-value. So that is represented by the lowercase letter p, which is typically italicized. And that represents the probability value, or to be more specific, the probability that the result you obtained was simply due to chance or error. And that p-value is always going to be between 0 and 1. So it will be a decimal. Now, this again goes back to the logic of sampling, because remember, when you only study a sample rather than the full population, there is always going to be a certain amount of sampling error. For example, if I wanted to know whether the SHIP student body is mostly Republican or mostly Democratic, and I went out and I grabbed 5 people, and all 5 of those people told me that they are Republicans, what does that tell me? Well, maybe it tells me that the SHIP student body is predominantly Republican, or it may have simply been a fluke. It may have been due to chance or error. Maybe it just so happens that the 5 students that I grabbed all happen to be Republicans, but they're not really representative of the overall student body. So anytime we study a sample, there's going to be a certain amount of error, or sometimes our results are simply due to chance. And it doesn't mean we did anything wrong. It doesn't mean we made a mistake in our research. That's just the reality of sampling. So the p-value will tell you what the probability is that your result was simply due to chance or error. And we obviously want that value to be as low as possible, as close to 0 as possible, indicating no chance that it was due to chance or error, okay? But it's never going to be 0. It's also never going to be 1. It's always going to live somewhere between 0 and 1, and we want it to be as small as possible. How small, you ask? Well, the usual cutoff is 0.05. Which would mean a 5% probability that the result you obtained was simply due to chance or error. Or to put that another way, a 95% probability that it was a real valid result that would be applicable to the overall population. Now, that cutoff of 0.05 is not etched in stone. It's kind of arbitrary. It's just over the course of years and years, researchers have more or less arrived at a consensus that 0.05 is the best cutoff point. But there's no law that says that has to be the cutoff point. You will see some studies that will set the cutoff value at 0.01, and you may see some studies that will set it at 0.10. But 0.05 is the usual cutoff point. So what does this mean? Remember, we want the value to be as low as possible. So if the value of p is less than 0.05, that is telling us that our result is statistically significant. In other words, yes, it probably would hold true for the overall population. We can have enough confidence in our result that we can say our hypothesis is supported. If the value of p is greater than 0.05, that is telling us that the result is not significant, and that there is a strong chance that the result we obtained was simply due to chance or error. So therefore, we cannot support our hypothesis. We have to reject our hypothesis. Now, like I said, this is not a cut in stone or etched in stone cutoff point. So you may be wondering, well, what if the p-value is 0.06 or 0.08? It's really close to the cutoff point, but not quite. Well, in a situation like that, we might say that our result approached significance, and we might say in the limitations section of our discussion section that there is a need for additional research. Understand that the p-value is always going to be very sensitive to sample size. So if you have a very, very small sample, it's going to be very difficult to obtain statistical significance. Whereas if you have a huge sample, it's going to be much easier to obtain statistical significance. So let's look at an example of this, which will hopefully help clarify how this works. So let's say that it was some kind of a study about how many hours students spend on different social media platforms. And you find that the mean number of hours that students spend on Instagram is 7.14. And the mean number of hours that they spend on TikTok is 5.26. So just looking at those numbers, you might be tempted to say, okay, I have just proven that students spend more hours on Instagram than on TikTok. Not necessarily, because you probably only studied a sample of students. In order to make that inferential leap, you need to know, is that difference, the difference between 7.14 and 5.26, is that statistically significant? So you would have to run a statistical test. In this case, it would probably be a t-test, where you're comparing the two means. And that statistical test would produce a p-value. Let's say the p-value is 0.23. So what does that tell us? Well, remember, we want the p-value to be as low as possible, and the cutoff for statistical significance is typically 0.05. So 0.23 is obviously greater than 0.05, which means the difference was not statistically significant. So what can we conclude? Well, we can't really conclude that there is any difference at all in the number of hours that students spend on Instagram versus TikTok. Because even though we did find a difference in our sample, the statistical test told us that that was not statistically significant. So we cannot make any real conclusions about the difference between hours on Instagram and hours on TikTok. We would have to reject our hypothesis. On the other hand, let's say you did the study and you got the same results, and you ran a t-test, your inferential statistical test, and this time you got a p-value of 0.03. What can we conclude? Well, 0.03 is obviously less than 0.05, which means that our result is statistically significant. So in this situation, we would go back to our numbers, and we see that the mean is higher for Instagram than it is for TikTok. So we can indeed say with a fair degree of confidence that students spend more hours on Instagram than they do on TikTok. And it's all because of that value of P, the probability value. So a number of statistics programs will allow you to run inferential statistics and will give you the results, including the p-value. You can do some inferential statistics in a program like Excel, but if you want to do more heavy-duty statistical work, you have to get into programs that are specialized for this sort of statistical analysis. SPSS is commonly used in the communication field. It is a statistical program that is produced by the folks at IBM. They actually acquired SPSS, I think, in 2009. SPSS is available on a lot of computers on campus. In a lot of other fields, they use other statistical programs as well, like SAS and Stata and R. So if you should decide to pursue a Ph.D. or some other program where you do a lot of statistical work, you may become familiar with one or more of these statistical programs.